Have you ever looked up at the night sky and wondered what's out there? Among the stars, some have already died, leaving behind mysterious remnants. These are the stellar ghosts, white dwarfs, the glowing embers of stars like our sun. Most are made of carbon and oxygen, but a rare few are even stranger oxygen neon white dwarfs. Imagine a star that's burned out, collapsing into a ball the size of Earth, so dense a teaspoon would weigh as much as an elephant. These Oni white dwarfs are the universe's rarest desserts, forged by stars that lived on the edge of possibility. They're cosmic enigmas, holding secrets about the most massive stars that didn't quite go supernova. Today, we'll explore how these stellar ghosts are born, what makes them so weird, and why astronomers hunt for them. We'll dive into the heart of stellar evolution, where elements are forged in a cosmic dance of creation and destruction. Let's get started. Every star begins in a stellar nursery, a vast, cold cloud of gas and dust called a nebula. Gravity pulls clumps of this material together, forming protostars that heat up as they collapse. When the core gets hot enough, nuclear fusion ignites, and a star is born. The star's life is a battle between gravity and the energy from fusion. Its fate depends on its mass. Small stars live long, quiet lives. Massive stars burn fast and die young. The most massive stars explode as supernovae, while low-mass stars fade quietly. But some stars fall in between, too big to die quietly, not big enough to explode. These are the stars destined to become oxygen neon white dwarfs. Their story is about being just the right size for a unique fate. They're the missing link between quiet endings and spectacular explosions. Let's follow their journey from birth to their extraordinary afterlife. This is where the path to Oni white dwarfs begins. To make an oxygen neon white dwarf, you need a Goldilocks star, not too small, not too massive. Stars like our sun end as carbon-oxygen white dwarfs, lacking the heft for more extreme fusion. Truly massive stars, over 10 times the sun's mass, go supernova, leaving neutron stars or black holes. The Goldilocks stars, with about 8 to 10.5 solar masses, are just right. These stars burn through fuel quickly, swelling into red giants as their cores contract and heat up. When helium runs out, gravity squeezes the core even tighter, igniting carbon fusion. Only these mid-mass stars can fuse carbon without self-destructing. This rare carbon-burning phase creates neon and sodium, setting the stage for an Oni white dwarf. The star sheds its outer layers, revealing the hot, dense core. What's left is a newborn oxygen neon white dwarf, a cosmic relic forged in fire. These stars are the universe's rarest survivors. Their unique journey makes them stand out among stellar remnants. Let's zoom in on the final act of our Goldilocks star. After helium is gone, the core, now carbon and oxygen, is squeezed by gravity to over 600 million Kelvin. Carbon fusion ignites in flashes, creating neon, sodium, and a bit of magnesium. This is stellar alchemy at its most extreme, transforming the core's composition. If the star were more massive, fusion would continue to iron, ending in a supernova. But here, the carbon-burning phase is intense but short-lived. The star undergoes thermal pulses, shedding its outer layers as a glowing planetary nebula. What remains is a naked, super-hot core, mostly oxygen and neon, with traces of magnesium and sodium. This core is squeezed into electron-degenerate matter, an exotic state where gravity is balanced by quantum pressure. The Great Squeeze is over, and a new Oin white dwarf is born. It's a fossil of a star's dramatic life, preserved in a dense, crystalline heart. These white dwarfs are rare, but they tell us about the universe's most extreme conditions. Their formation is a delicate balance. Too much mass, and they explode. Too little, and they never reach this stage. Oni white dwarfs are the ultimate survivors of stellar evolution's middle ground. What's inside an oxygen neon white dwarf? It's not like anything on Earth. The core is made of electron-degenerate matter, atoms packed so tightly their electrons form a quantum sea. At the center is a core of oxygen and neon, surrounded by a thin shell of carbon and oxygen. Above that, a shallow layer of helium, and an even thinner hydrogen atmosphere. The intense gravity separates elements by weight, making the surface pure hydrogen. Over time, the core may crystallize, turning into a gigantic Earth-sized diamond, though not the sparkly kind. This crystallization is a cosmic time capsule, preserving the star's history. When you look up, you might be seeing the crystallized hearts of ancient stars. Oni white dwarfs are cosmic diamonds forged under unimaginable pressure. What sets Oni white dwarfs apart? First, their mass. They're the heavyweights, close to the Chandrasekhar limit of 1.4 solar masses. More mass means a smaller, denser star, like a cosmic bowling ball. Their unique composition, especially neon, gives them an extra cooling mechanism, neutrino emission. Oni white dwarfs cool faster at first, thanks to these ghostly particles carrying energy away. But the biggest difference is their fate if they gain more mass. If pushed over the limit, a carbon-oxygen white dwarf explodes as a type Ia supernova. An Oni white dwarf instead collapses directly into a neutron star. No explosion, just a sudden transformation. This makes them a unique pathway to neutron star formation, bypassing the usual supernova. Their rarity and unique physics make them a key piece in the cosmic puzzle. Oni white dwarfs are the universe's most enigmatic survivors. After their fiery birth, Oni white dwarfs begin a long, slow cool-down. They start out blisteringly hot, shining in ultraviolet, but with no fusion, they gradually lose heat. Early on, neutrino cooling speeds up the process, making them fade faster than carbon-oxygen white dwarfs. As they cool, their cores crystallize, releasing latent heat and briefly slowing the decline. This crystallization is detectable, giving astronomers clues about their interiors. Eventually, after trillions of years, they'll become black dwarfs, cold, dark, and invisible. None exist yet. The universe isn't old enough. For now, Oni white dwarfs are cosmic embers, slowly fading but still holding the memory of their massive origins. Why do astronomers hunt for Oni white dwarfs? They're the missing link between quiet stellar deaths and explosive supernovae. Studying them helps us pinpoint the mass threshold that separates these fates. They're hard to find, almost identical to carbon-oxygen white dwarfs, so astronomers use clever techniques like astroseismology and cluster studies. Oni white dwarfs also help explain neutron stars that appear without supernova remnants. They're linked to rare type IAC supernovae, which may leave behind clues in their neon-rich debris. But there's a bigger mystery, a strange signal from the centers of galaxies that Oni white dwarfs might help explain. These rare stars could be the key to one of the universe's biggest puzzles. Let's get ready for the big reveal. Here's the twist. Astronomers have detected a mysterious gamma-ray glow from the Milky Way's center, a sign of matter and antimatter annihilation. For years, dark matter was the prime suspect, but the evidence didn't fit. Now, the spotlight is on Oni white dwarfs and the supernovae they can create. When these stars explode or collapse, they produce radioactive cobalt, which decays and releases positrons. These positrons meet electrons, annihilate, and create the exact gamma-ray signal we see. The source of the galaxy's antimatter glow might not be dark matter, but the rare deaths of Oni white dwarfs. It's a scientific plot twist, solving a cosmic mystery by studying the faintest stellar ghosts. The universe's secrets are often hidden in the most unexpected places. By understanding Oni white dwarfs, we unlock mysteries from the smallest stars to the heart of the galaxy. That's the wonder of science. Every answer leads to new, even bigger questions.